Oh, hey. I was just looking at something about quicksort. See, quicksort, simply put, is a fast sorting algorithm. It uses big O notation to make comparisons between two numbers to sort them. It sorts recursively, meaning that it repeats the rule over and over again. It does this using what is called a divide and conquer method. In the divide and conquer method, the problem is broken down into subproblems. The subproblems are then solved, and then the solutions to those subproblems are then input into the original problem, all producing a simple sorted array in the end. My name is Matthew Hester, and I have a group assembled for you all today to talk to you more about quicksort. So let's go meet them. Oh, great, you all made it. How's it going, guys?
Oh, hey, how are you?
All right, so I got you all together so we can talk about the quicksort. So first things first, who we got here?
I'm Marcus Jeffrey.
Jasmine Harper.
I'm Edward Hill.
Christopher Haskins.
All right, so who's going to start off the discussion?
Matthew, I'm going to take it from here.
All right.
This array represents a list of 7 numbers that needs to be sorted quickly. As previously explained by Matthew, the first step in this algorithm is to divide and conquer. To do this, we need to find a pivot point. The pivot point is essentially a random location in the array with its value returned. This location is used to split up the array into less than and greater than sectors. In this example, created by Marcus, the random pivot point is 4. As the animation progresses, the value of P1 and P2 changes to satisfy the algorithm's conditions located in the text box below. The current conditions make the function recursive by allowing the movements of numbers in the array. When the conditions are met, the next step is to swap P1 and P2. In the current scenario, the 4 being P2 and the 7 being P1 satisfy the conditions and are thus switched. After the changes have been made, the 4 now divides the array until the less than and greater than sides. When P1 and P2 equals the same location in the array, that number is in the proper location in the sorted array.
Since 4 is now our pivot point, 2 partitions are formed on both sides. The left side is less than the pivot, and the right side is greater than the pivot. First, we begin with the left partition. We assign P1 and P2 to the outermost ends of the partition. The pivot is 2. We compare P1 to P2. Because P1 is less than P2, we have to swap them. Let's take a look at the pseudocode. Here we have a temporary variable called temp. We store P1 into temp, set P1 equal to P2, and then set P2 equal to temp. And that is how P2 replaces P1 if P1 is greater than P2. So now that P1 and P2 have switched places, 1 is in its final position. So now both pointers are pointing at 2, which means P1 equals P2, so now the array is locked into place. Now the partitions are formed around 2 and 4. Now that the left partition is just one number, 1 is now locked in place. So now we are just left with the right partition.
Notice that each time a new partition is made, a pivot is chosen within that partition, and P1 and P2 are set as bounds for the partition. With each execution of the while loop shown in the pseudocode below, it moves both pointers closer to one another. When it finds a number that's located on the wrong side of the pivot, it switches it to its correct side. Numbers larger than the pivot must wind up to the right of the pivot, and numbers less than the pivot will wind up to its left. When both P1 and P2 are both pointing at the same index location, it knows that this number is in its correct place. Therefore, it will lock that element in that location. Again, whenever we come along a partition with a size of 1, we know that that partition is considered sorted. Now all that's left is a partition of size 2. A new pivot is selected, and it is then compared to both P1 and P2. Now that both pointers are pointing at 11, that element is considered sorted and is locked in place. Now all that we have is a partition of size 1 remaining. Since it's of size 1, we know that that partition is considered sorted. And now that we have no partitions left to sort, we know that the entire list of numbers is now sorted.
And there you have it. Once P1 and P2 collide, the remaining partition will be the number that you will need to complete the unsorted array. Hopefully this presentation will help you understand quicksort even better. Thank you for watching and have a good day.